Hello students. So today's question says a particle of mass m is kept on a fixed smooth sphere of radius capital R at a position where the radius through the particle makes an angle of 30 degrees with the vertical. The particle is released from this position. What is the force exerted by the sphere on the particle just after the release? And find the distance travelled by the particle before it leaves contact with the sphere. So, this is the figure as shown here. Initially, the particle is at position A, where it just starts off from rest. So, for the first part of the question, since we know that the velocity at the point A is 0, right, along the radial direction, then the net forces must be 0, because along the radial direction we can always write F centripetal is equal to mass into the centripetal acceleration, which by definition is v squared by r. So, since v is 0 at the point A, we can say that the net force along the centripetal direction, along the radial direction, must also be 0, right? Now, what are the forces acting in this direction? If we look at the forces acting on this body, there will be a normal reaction acting in the radially outward direction as shown here. And the only other force acting on this particle is gravity, mg, which will act in the vertically downward direction, right? So, if we take the component of gravitational force along the radially inward direction, it will be mg cos 30, because this angle is also going to be 30 degrees. So, that we can say that this component of mg cos 30, the radially inward force, should exactly balance the radially outward force, which is n, right? So, from here we directly get the value of n as mg into root of 3 by 2, which is the value of cos 30. So, this directly gives us the answer to the first part. Now, for the second part, we are asked to find out the distance travelled by the particle before it leaves contact with the sphere. So, let us assume that this particle leaves contact with the sphere when it reaches this new position C, which makes an angle of theta with the vertical, so that the particle moves from the point A to the point B, and it is at the point B where it leaves contact. So, first thing that we can do here is we can find out the speed that the particle gains at the position B, right, by using the law of conservation of energy. And once we get the speed, we can use the same formula for the force along the radial direction, n outward and mg cos theta inward, and this time we can say that since the body is leaving contact, n will go to 0 at the position B, right. So, first we shall use the conservation of energy between the points A and B, where we can say that whatever potential energy the particle has lost between the points A and B, corresponding to this height h through which the particle has moved down, the loss of potential energy, which will be mgh, should be equal to the gain in kinetic energy, which by definition will be the final kinetic energy half mvb squared minus the initial kinetic energy, which is the kinetic energy at the point A, which we know is 0. The particle started off from rest at the position A. So, from here we can substitute the value of h in this expression. Once again, by using this figure, do we all see that h will be nothing but this length minus this length. Now, the first length that I drew here is nothing but r cos 30. This bigger length here is r cos 30 degrees, and the smaller length is r cos theta. So, h comes out to be nothing but r cos 30 degrees minus r cos theta. Okay. So, when we substitute its value over here, we will get m. Okay, by the way, m we can cancel out here so that we do not have to write m. So, we will have g into r cos of 30 minus cos theta is equal to, and this 2 can be taken on the left side, so that this becomes 2 gr. This is our value of vb squared, the speed at the position B. And the second thing that we can do is we can use the force equation at the point B along the radially inward direction, saying that since the normal force is 0, it is only mg cos theta which is providing all the necessary centripetal force, which is equal to nothing but m into Vb squared by r. And now we can substitute the value of Vb from the above equation here and solve this. So we have m getting cancelled here, and we are getting g cos theta with r being taken on the left side, so it will become rg cos theta is equal to, substituting the value of Vb squared from this above expression, we will have 2gr into cos 30 minus cos theta, which can now be solved for the value of theta. After solving this, you see that rg gets cancelled and we have cos theta on the left side and 2 cos theta on the right side. So, we will have a 3 cos theta is equal to 2 times cos 30, which is nothing but 2 times root of 3 by 2. 2 will cancel out, the root 3 will also cancel out, and we will get cos theta is equal to 1 by root 3, or theta is equal to cos inverse of 1 by root 3, whose value can actually be calculated from trigonometric tables, and this value nearly comes out to be 0.95 radians. Okay. Now, once we get the value of this theta, we go back to what we are supposed to find out. We are supposed to find out the distance travelled by the particle. That means we want to know this arc length from A to B. Yes, understand that the formula for arc length across a certain angle, arc length is given by r into phi, where r is the radius of the circular path over which the particle has moved and phi is the angle through which it has moved. So, in our case, in our question, it is r into, see that the total angle phi that the particle has travelled will be theta minus 30 degrees. Theta minus 30 degrees, which in radians we can write as pi by 6. So, substituting the values, r into theta is 0.95 radians and pi by 6, if we calculate in radians, it comes out to be nearly 0.52. So, that our answer comes out to be nearly 0.43 times r, which is the final answer.